Good morning to all of you. Hello. Okay. Mm. Just so in this class, we are. This is the second class on semiconductor, and the basic thing about semiconductor is that we learned about the charge carriers in a semiconductor, that is electrons and holes, in contrast to metals where electrons were the only charge carriers. Here we also have additional charge carrier H plus, that is holes. The vacancy that is created by electron in the valence band is treated as uh, a positively charged particle, and that is called hole. And that hole also moves in the reverse direction. If conduction in the conduction band, if you have movement occurring in, the energy increases as you move up. For the hole, energy increases as it moves down the valence band. So that is how the movement occurs. We also discussed the E versus K relationship and how we can find the effective mass. So these are the things that we discussed. And this effective mass is a, a concept that comes into picture. Even the mass, सिंपल जो मास कहते हैं ना, वो मास भी हमें थोड़ा और फंडामेंटल लेवल पे जाके देखें तो दैट वाज just a proportionality constant when the initial the force is proportional to the acceleration when view it that way. And if it is in vacuum, you are putting some particle with having no other forces around it, no other interactions, then the proportionality constant is mass. We call it mass. If the same particle is in a, say, matrix, in a state where you have several other atoms, several other um, particles around it, that is the case in a crystal. So electron in a crystal will behave differently when when the force is applied. The acceleration that will be produced will be different, and so the proportionality constant is also going to be different. So when we start with force is directly proportional to A, the proportionality constant changes here, and that is uh, called effective mass. This proportion. So earlier in the rest, if the particle is on rest, electron is at rest, and you uh, apply this Newton's law and introduce this proportionality constant, that is mass, rest mass, and here it will be called effective mass. So it is in another way it will be visualized as if the if you are having a electron in the crystal, and somewhere, as I told you, there is a periodic potential across the crystal because of periodic arrangement of the atoms. They have positively charged cores, that is nucleus, and so if you look at the arrangement, there will be a variation, periodic variation in the potential as it moves through. So it is possible that at some point when you try to you apply a force on the electron, try to take it out, you'll feel that it is heavier than the normal case. If in some other part of the crystal, you might find that it is uh, much easier to take out the electron as compared to move an electron from the its initial position. So that apparent चीज, मतलब कोई नीचे से push करे तो आपको वही चीज हल्की लगेगी, कोई खींचे नीचे की ओर तो आपको उठाना मतलब लिफ्ट करना मुश्किल हो जाएगा सर। तो उसी तरह से यहाँ इलेक्ट्रॉन का भी केस है, एंड दैट्स हाउ वी दिस mass that is we call is effective mass here, that is the altered mass. So because it is when we have a bound system, we always take the effective mass. For bound system, bound state, we always take effective mass into consideration whenever we apply uh, whenever we try to understand the motion under influence of certain force. We do take this into account. So periodic crystal, yeah. So the effective mass is mathematically, I told you that it is possible to find in a very simple way. How to find? You look at the E versus K plot, find the curvature, and this curvature, that is so this is the curvature. So h cross square by the curvature of the thing. So it is inversely proportional. When the curvature is high, mass will be low. When the curvature is less, effective mass will be high. So depending on the band structure, it will the effective mass can change. Okay, so effective mass is a double derivative of E, and so this effective mass is yeah, as I told you. So different directions will have different effective masses, but what we do is we use average. We take the average, and for most of our work we use this average value of the effective mass. And that, to give you an idea, this is the thing. So effective mass of electron in silicon is uh, 1.1 m naught. That is, as compared to the rest mass, the mass here is slightly greater, but in gallium arsenide it is less. In germanium, the effective mass of electron is less. So like that. And this mp, the positively charged particle, that is hole. So you have it is, in all cases you are finding that it is less than the effective mass, the rest mass of electron. So electron and holes both behave as waves, and standing waves rather, because they are bound system. Bound system हमेशा standing wave ही बनेगा. And so they can also satisfy, they can also undergo diffraction just as X-rays, and they must also satisfy these conditions of the diffraction, the Bragg's condition. The lambda will be different because of the electron here. So certain so k gives you the value of kh cross is the electron momentum. K is, so h cross is constant, k is the, from system to system, one semiconductor to other, k will vary. So kh cross is the momentum, and certain momentum will not be allowed because for the in the crystal lattice. So that is the origin of gap, band gap in another way. So 2 pi by k, n lambda should be equal to 2d. This is a simple 2d sine theta. If, so p square by 2m, we know this energy of electron, we have already found that. So what we have here is, this is equation 1, equation 2, and when we put it together, we can substitute lambda So we have already okay, sorry, this thing we have already discussed. Mass is the determined from the curvature, inverse proportionality, so h square by m. So using this relation, so this is your thing, effective mass. To find an effective mass in the crystal, we use the h cross square by curvature. Curvature can be positive or negative, so the mass can also be positive or negative. That can happen. Okay, so now we the based on the band gaps, nature of band gaps, we can classify them as indirect or direct band gap. Direct band gap semiconductors, indirect band gap semiconductors. So, so the example that has been shown over here, in a direct band gap crystal, if you look at the valence band and conduction band, the maximum of the uh, valence, the top of the valence band. So this is top of the valence band. We call it TVB, top of the valence band. This is bottom of the conduction band, bottom and top. So bottom and top both are at the same value of k, at the same value of k. So that means during the transition, when the electron goes from valence band to conduction band, uh, during the transition, del k is 0. Del k is 0. So the momentum is conserved. Crystal momentum is the momentum of the electron is conserved, and this is gives rise to what you know as the selection rules. So conservation of momentum again is telling us that for the transition to occur, k should not change when electron moves from valence band to conduction band, and under these conditions the absorption of light or emission of light would be much better. Interaction between the photon interaction with the photons would be better. So example that is given here is for the emission to happen. So emission means you have electron is already excited by some means to the conduction band, and that is sitting over in the conduction band that's shown in the blue color electron, and the vacancy created is plus sign, that is hole. So what you see in the picture is, so this is an example of direct band gap semiconductor. So looking at the band structure, looking at the E versus K plot of a for semiconductor, we can identify whether they are direct band gap or not. So electron that is at the bottom of conduction band, uh, it may recombine with the hole that is at the top of the valence band, and there is no change in momentum. This leads to, in the process you will have, sorry, emission of light. So here, as it comes down and recombines, there will be h mu, photon will be emitted, emission. So this is the idea when we choose, when we have to so light is emitted, and we call that such transitions where photon is emitted, light is emitted, we call it radiative transitions. Radiation is given out, electromagnetic radiation, so we call it radiative transitions. So direct band is direct band gap material. When we say a direct band gap semiconductor, we mean that it has this kind of structure where top of the valence band and bottom of the conduction band lie at the same k value, and so such materials will have very good uh, what we say light matter interaction, sorry, good light matter interaction, because they follow the selection rule. They The conservation of momentum is done when the photon interacts. On the other hand, you also have situations sometimes in many semiconductors, the bottom of conduction band and the top of uh, bottom of the conduction band, that is here, and the top of valence band are not at the same k values. K value is different. It is located at a different k value, and this is so. In such cases, when you have the lowest possible energy transition, that is the band gap transition, e.g., if you are trying to make it will be difficult because the momentum is not conserved. Looking at the simple absorption or emission of a photon, there will be the momentum will not be followed, and if any absorption occurs, it has to take the to conserve the momentum, it must take the help of phonons, the lattice vibrations. The lattice vibrations come assist. So क्या होता है कि इलेक्ट्रॉन वेट करता रहता है. मान लो कि ये जो अभी हमने पिक्चर दिखाया एमिशन के लिए, अगर लाइट एमिशन चाहिए हमें ऐसे, सो द लैटिस इज वाइब्रेटिंग and this electron will go here, combine with the hole uh, and emit light, but the momentum is not being conserved. So अकेले में तो ये प्रोसेस नहीं होगा, लेकिन जो लैटिस वाइब्रेशन है, द फोनॉन्स, they can carry some momentum, they can get involved, and so मतलब continuous vibration हो रहा है, the electron is sitting at the bottom of conduction band and it waits for right kind of phonon to turn up at a particular moment, and then it can go back to the valence band and light can be emitted. So it is a phonon assisted process. सो ये बहुत कॉम्प्लिकेटेड होता है कि उसको वेट करता रहेगा कब वो वाइब्रेशन उस पर्टिकुलर उतने मोमेंटम का आएगा, फोनॉन आएगा और उसको द कंजर्वेशन ऑफ मोमेंटम विल बी फॉलोड एंड द प्रोसेस विल अकर. सो this such band gap, so this is called indirect band gap, and such materials have poor light matter interaction. That means absorption emission will not be good. So जब आपको अप्लाई करना है, when you are thinking of applications, so such materials are having poor, so what I in one word I will say, light matter interaction is poor in this case because k for top of valence band, k for bottom of conduction band not equal. So del k is not equal to 0 during if we are looking at the band gap transition. So momentum not conserved, that means momentum not conserved, and that's why they have to the if momentum is not conserved, this process is not going to happen. So if somehow kuch somebody helps you, then only so phonon comes to the help, phonons comes to the rescue, and some absorption or some emission, if the electron is already at the excited state, can happen with the help of phonons. Phonons is the quanta of the lattice vibration, phonons are the quanta of the lattice vibrations. Okay, when we are visualizing vibrational, we write vibrational wave function, we also visualize these lattice vibration as waves. So that vibrations inside the crystal helps to conserve the momentum in this particular case, and then only it happens. So एक तीसरे की हेल्प लेनी होती है, एंड सो ये प्रोसेस बहुत वीक होता है, एब्जॉर्प्शन बहुत कम होगा, लाइट का एमिशन भी ना के बराबर होगा. सो Such materials which do not have good light matter interaction, so they will not be good for making of LEDs. अगर आपको light emitting device बनाना है, so you will choose a direct band gap semiconductor rather than indirect. Indirect band gap material are not suitable for light matter interaction. That means they have poor emission, poor absorption properties, poor absorption of light, and so poor emission of light. So they are not good for this thing. So phonons, as I told you, phonons, when we are talking about lattice vibration, when we are visualizing that as one quantized vibrational waves, they have, so as long as they exist only in the bound state in the crystal. Okay, so that's the thing that we have considered here. Pure light. So two types of, so such transitions will involve, so there are chances that radiation may not be emitted at all, and it will lose energy by transferring the electron will come to the ground state in this case by providing transferring energy in a small amount to the lattice vibration. So that can also happen, and that is called non-radiative transition, where no emission of light will happen. So such indirect band gap, so they are inefficient, for they are not good for making of LEDs or lasers when you are trying to design. Okay, so one should always choose a direct band gap material such as gallium arsenide or something like this. Um, so so photon and phonon, so this is, so taking example of gallium arsenide, you can get the idea of how different the energies are. Okay, so gallium arsenide, so typical band, taking the band gap energy, so band gap in photon, in gallium arsenide is 1.43. So you can calculate the lambda, which is around 880 नैनोमीटर, 880 नैनोमीटर है वेवलेंथ, और फोटोन का जो मोमेंटम है वो यहाँ पे दिया हुआ है. Similarly for phonons, if you try to calculate, then you have to incorporate velocity. So actually these lattice vibrations, when you visualize them as a one quanta of that lattice vibration is called phonon. They have a velocity which is corresponds to the velocity of sound, and that is the why it is called phonon. Phon means sound, this means sound, and because it is the lattice vibrations, the quantized, the vibrational wave that we can visualize in a lattice, one quanta of that has a velocity that is the speed of sound, and so it is, we called it phonon, it was called phonon. Okay, so energy of that one phonon, if you compare, is much less, is 0.037. So huge difference, 1.43 eV is the gap. So photon will have this much energy to excite the electron, and in comparison the energy of phonons is much less. And 37 milli electron volt. Photon momentum is this much, and phonon's momentum is much higher. So momentum of the phonon, if you compare, so this is what we found in the previous slide. So photon carry large energy but negligible amount of momentum. Photons. So this is what we can see very clearly. Large amount of energy but negligible amount of momentum. phonons carry very little energy but significant amount of momentum. So this is also a interesting point that we see here. So effective mass we have already talked about in previous slide. Through the E versus curvature of E versus K, we can find that. So particles sitting near the minimum. So now look at the positions and think of the curvature. So particles sitting near the minimum of the, so like positive effective mass, whereas, so if you're looking at the so if this is the situation, you have electrons sitting near the bottom of conduction band. So in this case the curvature is positive and you have positive effective mass. And for the holes, these are the holes, sorry, so these are holes, hole, and this is sitting near the valence band, top of the valence band, and this will, here the uh, d2e by dk, this will be negative, the derivative will be negative for this, and so uh, it will have negative effective mass in such situation. So a negative effective mass means that you apply force and it moves in a reverse direction than what you expect, in a direction that is different from the, so that is the meaning of that is it moves. So a negative effective mass means that the particle will go in the reverse direction or in the wrong way when the force is applied. So that was the kind of uh, conduction band on valence band, the kind of parabola that we were showing earlier in all our curves, in all our graphs, on all our slides. That is a simplification, a simplified view of the band structure. In reality, the band structure may look like something very complex, and look like this. It may look like something like this. And so for gallium, so this is the real, when thorough calculation is done, this is the real band structure E versus K curve for sorry, for the gallium arsenide and silicon. So what we see here now, that, so this one is the position, the top of sorry, bottom of the conduction band. This is our bottom of the conduction band, BCB, and this is the top of the valence band, top of the valence band, and so this is our band gap, right? In a similar way, if we are looking at the silicon crystal, uh, this is the top of the valence band, and bottom of the conduction band lies somewhere here, bottom of the conduction band. So band gap is, so see, the K value is different. So here, if you are looking at top of the valence band, bottom of the conduction band, different K. K value is different. So K is momentum is not full, but here the top of the valence band both are existing at same K, same for both top of the valence band, bottom of the conduction band. So this is a direct band gap, that is direct band gap, and this one is having indirect band gap. So this is the picture of a very intense calculation, quantum mechanical calculation, that gives you this kind of band structure, understanding of the system. So actual band structure looks much more complicated. But in a very simplified view, we take it as a parabola, conduction band, valence band, and simple compare it, make comparisons. So you are also aware why we are putting it like this. You have already seen that for s orbitals we were having this kind of parabola was coming for s band when we considered combination. You also know that for p bands we had the reverse way. So this was the p band, and so if so this is the picture that you see. Something like this is happening here. So s band, p band. So this kind of structure, while studying metals, band theory of metals or any, so that theory was common to all. The same band theory applies to whether all solids, whether it's semiconductor or metal or insulator. Okay, so the profile in previous classes we have already discussed about it. The S band looks like pretty much like this curve, and this is the P band, something like this will happen. So or vice versa, the situation may be different. S to P. So this is the situation. So band gap, when we talk of band gap, it is the smallest energy separation between the valence and conduction band edges. So so we also call it as conduction band edge. जो हम bottom of conduction band कह रहे थे, in another word we can also say conduction band edge, CBE. edge मतलब किनारा होता है, E for edge, and this we can also call this as valence band edge. So edge to edge difference is your band gap, valence band edge. So नदी है, दोनों किनारे को आप edge कहते हैं ना, टेबल का किनारा. हाँ, so edge is the एकदम bottom वाला point या बिल्कुल top वाला point. So edge to edge difference is your band gap, the smallest energy separation between the edges, conduction band edge and the valence band edge. So if occurs the same momentum value, we have seen is the direct band gap. Gallium arsenide is an example of direct band gap. In contrast, when this is not so, that is the case of silicon, we call it as indirect band gap semiconductor. Minima of the two conduction band minimum and the top of the valence band do not match. They appear at the different k values. That's what they say. And so what we see here is that we are again going back to the roots and trying to find the transitions, why certain transitions are possible, certain others are not. So again, remember that we had while deriving selection rules, I told you there are two types. One that tells you about the interaction with the light will occur or not. So we need to have a transition dipole developed during the as the electron moves from valence band to the conduction band, and then only there will be interaction with the electric field vector of the. So this is a transition dipole. So initial to final wave function. So transition dipole must be developed, and this will interacts with sorry, electric field of light. Okay, so electric field vector of light is this is needed. Without this, there will be no interaction, there will be no absorption or emission of light. Okay, irrespective of whether you satisfy the second condition that del k is 0 or anything. So if we look at the, we have already considered the combination of p orbitals and making a p band. So we know this part, that so the S combinations, the if it is the initial, psi I means initial, and the final, this is psi F is the final. So this is the representative of the valence band, and this is the energy orbital at the bottom of conduction band, So this is, and the wave corresponding wave function is like this. So in this particular case, when they are arranged, the p orbitals, this is the p band, so example of a p band. So bottom of conduction band, so this is example of p band, and this is s band, just. And now the transition happens. So what we see, that when s orbital of a s band transformed into an orbital of a, when the wave function changes from psi I to psi f. So this is what is happening. This drawing is for the angular part of the wave functions, and when we look at the wave profiles, this is how the changes occur. And in this particular case, when this kind of, so this is the mu if that you are seeing here. Mu if is, this is the if is the dipole, transition dipole that will develop. So looking at the each one of them, when you are S to P kind of thing is happening, S to P, so each individual dipoles add up, and you have overall net. So these arrows that you see are the dipoles. So overall, when an orbital at the top of valence band, say S band, transform into another orbital at the bottom of the p band, as shown here, the wave function changes in this manner. There is asymmetric migration of charges, and so and each one of them will, when we look at the individually, each one of them generates a small dipole moment which adds up, and net there is net transition dipole developed. Okay, so a transition dipole is developed, and this transition is possible. Transition dipole is developed, and so when this is also k is 0, so del k is, so when del k is 0, we also find that a transition dipole is developed. Interaction will occur, and if you look at the other way around, when you do not have a, this is not so, when the situation is different, and so suppose the transition is from psi I initial, we keep it the same way, and the final, suppose it is like this. Suppose if somehow something, another situation, that the orbital at the, so final, this is the top of the, suppose it is the valence bottom of the conduction band. Suppose if this is the situation, top of the valence band, and so this transition that we are making, if this is the, so a wave function from that situation, so those kind of orbitals are transforming into another set of orbitals which are like this. Okay, and for that, in the initial case k was 0, in the final case the k is not equal to 0. So look at the picture here. If you look at the individually from here to here, there is a dipole in this direction. Now the other, so look at this. So for this s orbital, this was this shaded area that we represent is for plus and minus sign. So if all of these plus and minus sign of the wave function, these are the sign of wave function, sign of psi wave functions. So sign of wave function, so here in this particular case the orbital arrangements are different. All the p orbitals are in the anti-parallel thing. So see, they are different. So when if suppose going from this when this orbital was getting transformed into this orbital like this, it was direction of dipole was here. If this orbital is transforming in other way around, symmetrically slightly different, the dipole will be pointing in the opposite direction. So each of these orbitals is now, so these two dipole is pointing in the opposite direction, and here this is an opposite. So net dipole is 0. So when we look at this, the net dipole developed is 0. Dipole moment is 0. No dipole developed. So transition dipole here is 0, and so no interaction with light is possible in such case. So all such situations where you find, so you take any two sets of orbitals and compare, you will come to know what transitions are possible, what are not possible, and yeah. So this is, so other examples are given like here. नीचे कट जा रहा है, एक मिनट रुको. So when, okay, so other examples if you can take, so final, so you can change the initial and final thing. So if you take this one as the initial, where both are antipole, so plus minus, so you see plus minus. So now the s orbitals, if it is was plus sign, this is of minus sign, minus sign, plus sign, so that is at k is equal to pi by a, the most ideal. So consider a transition from that orbital to the orbital of this type, pi by a. So again, going by this, you have the dipole that is developed is so consider transformation of each of these s orbital in combination to a p type or p orbital, and so you have net dipole. Individually you can calculate and you can see simple profile. If this one is pointing in this direction, this one is also pointing in the same direction, so overall they add up, and transition net dipole is there. So transition dipole is there, moment, and not equal to 0, it is something non-zero value, and so light will be absorbed. Transition. So there are two considerations. One, develop whether the transition dipole is there at all or not, and then if the transition dipole is strong enough, very strong, then absorption will also very good. You will see intense color appearing in the substance because of good absorption of light. If the transition dipole is weak, you will have weak absorption. If the transition dipole is 0, there will be no absorption. So that is what we say, that certain transitions are allowed, certain transitions are uh, allowed and appear as with high intensity or low intensity. So those things depend on dipole. So now you got two, you now know the thoroughly two things about the selection rules. One, that del k should be 0 because to conserve the momentum of the crystal, to momentum, electrons momentum within the crystal. Okay, so that was one. And second, when we analyze the transition dipoles, we find that only when del k is 0, only when del k is 0 in this transition, del k is 0 in this transition, del k is 0. Oh sorry, कहाँ गया? So only when you have del k is 0, del k is 0, so only in under these conditions net dipole is developed, and you have net transition dipole is developed, and so this transition dipole can interact with the electric field vector of the light, and absorption or emission will happen. So this is the summarized in this slide. It is written, the details of which is given here already. So dipole moment is crucial to know whether transition will happen or not. So the integral that we were seeing must be integral that we were seeing sorry the transition integral must be non-zero. Okay, so transition dipoles on each atom. So it was what we have shown in the previous picture was the transition dipoles atom by atom, developing from one atom to the other, that are seen arranged in the crystal, and then summation of those individual transition dipoles when we are looking at them, and then sum it up over the entire crystal. So K0, what we have seen earlier is that yes, whenever you had K0 state up to K0 state in the P S band to P band, we found that atomic transitions are all in phase. Electric field so will come, they will interact with the electric field to give a non-zero value of the transition integral, so transition will occur. So now we look at a very interesting point of tetrahedral solids. Analyze the band structure in carbon, silicon, germanium, and tin. So what we see here, uh, carbon. Carbon is an example where we know that S and P, the 2s and 2p orbitals are very close enough. There is a good interaction between them, and hybridization is good. So when the when the interacting orbitals interaction between the orbitals is good, you have hybridization, and these hybrid orbitals are used for bonding. So instead, so you have a sp3 bonding orbital, set of sp3 bonding orbitals that will constitute the valence band, sp3 anti-bonding orbitals that will constitute the conduction band. So that is the case in carbon. If you are visualizing the diamond structure, silicon tetrahedral, so silicon in this, and so on. So but as we go down the group, go down the group, this interaction between s and p orbitals will become weaker. The hybridization is not strong, and finally by the time we reach Sn, tin, this is the turning point. It is very very big, and individual s band and p bonds will start forming. Instead of a sp3 hybrid orbitals being used for bonding, if only pure s orbitals are used, pure p orbitals are used, you will have formation of s band and p band. So that is what is reflected, and by the time you reach tin, tin lead. So tin is very close to the crossover point. So in the structure that we see here, in the tin, in the case of lead, we will have clear S band and P band, and S band will be, in case of tin, what is the electronic configuration is P2, sorry, S2 P2. So S band is fully filled. So this gives you S band is fully filled, and the P band, when you construct, it will be half filled, and so you will it will be metallic. So the behavior, so the P band, looking at the electronic configuration of the lead atom, and the orbitals here are not good. There is good separation between S and P energies, so they are not undergoing hybridization, uh, and s orbitals are lying low in energy as compared to p, much lower in energy, and p. So s orbital combines with another s orbitals to give you neighboring from the neighboring atom, giving you a s band and a p band separately. So s band is fully filled, and the p band, when it is formed, it will be half filled. So if we construct from p orbitals, p to one third filling, p band, when we construct 1/3 filled, so it is less than half filled, and in the band structure you have availability of several uh, energy levels with no cost of energy. Continuum of energy levels are there, so it will be conduct metallic, it will show metallic behavior. So this is the idea that okay. So all these things are discussed here. So basic thing that I'm trying to point out here is that just like you have uh, so imagine you have silicon. Silicon will use visualize a silicon crystal. In a silicon crystal, each of the silicon atoms will utilize sp3 hybrid orbitals, and there will be formation of bonding molecular orbitals and anti-bonding. So this is something that you can, so if you just think of this way, what, so what I was saying, that if just like we have followed the scheme for sodium, lithium, magnesium while making the bands, we can similarly construct this for silicon crystal. uh, a crystal, if you try to, what will happen? So if we have two silicon atoms, so they will be using sp3 orbitals. They will use each of the silicon atom will have sp3 hybrid orbitals, and that will be used for bonding orbitals. And when we are talking about this, so sp3 hybrid orbitals, when they are used, uh, so you can think of one silicon, two silicon atoms. So this is what you already know. So suppose this is the sp3 hybrid orbital of one silicon, another silicon, 1 2 3 4, 1 2 3 4. So sp3 hybrid orbitals of silicon, another silicon, and when they try to form bonds, so so between any two, bonding, anti-bonding will be there. Bonding MO, anti-bonding MO. So anti-bonding molecular orbital. So in this way, if you go on increase the number, so instead, as I told you, that we cannot, when we have more than two atoms, it is difficult to show in this, that how will you set. So instead of showing this full side, we show only this part and write the number of atoms on here. So we show this one, bonding and anti-bonding with, so bonding MO, anti-bonding MO, and we write here the number of atoms total Si2. So when we have Si3, you can imagine the same thing will happen. So you have 3 orbitals will be formed, which will be, so rather we'll take this Si2, 3, Si4. If you think of 4 silicon atoms combining, then there will be 4 set of molecular orbitals will be formed, 2 anti-bonding and 2 so bonding MO, anti-bonding MO. And so in a similar fashion, if you go on increasing the number of atoms, finally you will have a situation where uh, so finally you will have a very large number of silicon atoms are present in a crystal. There, if you extend this pattern of bonding, then you will have a very large number of anti-bonding orbitals available. So this is one, and you also have a large number of bonding MOs, anti-bonding, bonding MOs, and this there is energy gap. So this is the, so this, we are using sp3 hybrid orbitals in this entire combination, hybrid orbitals. So all these energy levels are combinations of sp3 hybrids, combination of sp3 hybrids that is leading to such thing, anti-bonding and bonding. So starting from some set of material orbitals, we get a band-like structure. One band which is completely bonding in nature, another set of orbitals are formed which are anti-bonding in nature, and there is separation between the two. So this kind of thing is what we obtain in this, and so all these things are there in the book by P.A. Cox that you read. So this is the thing that you see on screen is actually that thing. So S2P2 electron that we are talking about in when we are talking about lead down the group, there is the separation between S and P orbitals in terms of energy within an isolated atom also is much greater, and S orbitals electrons do not take part in bonding, that we also know as, so because of their lowered energy they have a less tendency to participate in bonding. We call them inert pair, and that effect is clearly reflected in the band structure also. There is also mixing and redistribution of energy. The hybridization do not occur between S and P. As we move down the group, the interaction strength decreases, and so that was the idea that this picture was conveying. This picture conveys that idea that you have a increased band gap initially. So this is a gap in carbon, which is a insulator. This is what is this? This is a diamond, tetrahedral solid. That means we are talking about diamond. So that is insulator. Then you have silicon, which is much lower gap. So that is, in case of silicon, you have, this is the gap, reduced gap. This is a semiconductor, silicon crystal. Germanium has even smaller gap. So gradually the strength of interaction decreases, and so the separation between bonding, anti-bonding, and that finally the separation between the conduction band and valence band is decreasing as we are moving down the group. And finally, by the time we reach tin, there is almost very less, the hybridization is not good enough, and you have intermediate situation. It is very close to this point, crossover point. So this is what we know as the crossover point. We call it crossover point. What is the crossover point? It shows the point from where, when we are moving down the group, there is decrease in the strength, bonding strength. Okay, the interaction between the orbitals becomes poorer. uh, Initially we had sp3 orbitals when we start with carbon, very good interaction. So interaction is good, so separation between bonding and anti-bonding is more. As we move down the group, the interaction between the hybrid orbitals decreases. So in silicon there is less gap appearing between a set of anti-bonding orbital and bonding orbitals. As we move further down the group, this S and P interaction is much less, and finally at a point beyond this point, when the interaction between is poor enough between S and P, what happens is that a separate S band will appear. So beyond this point you have mixed. So beyond this, to this side, you have separate S and P band being formed. Separate S band, P band is formed, and to the right hand side of this point we have sp3. So separate S band and P band. Here we have, on this side of the crossover point, we have uh, anti-bonding set of sp3 band. Okay, and we also have bonding sp3 band. So sp3 band, which is, and there is gap. Okay, so this happens on the other side of this. So this is what we call as crossover points. So if you look at the atoms and gradual moving down the group, you have a point, depending on the strength of interaction between the orbitals, strength of the bonding, that at some point S and P do not interact. The separation, there is separate, no hybrid orbitals are formed, and so there's no, so the band structure goes a very is very different. Now the S band will be completely full, P band will be half filled, and so you will have metallic properties appear on this side. And even in the atoms which are very close to this crossover point, metallic property appear. So even tin shows slightly metallic properties, and lead on this side will definitely have a much, it is metallic, that we know. Okay, so that's the crossover point we were talking about. So all these things, mm, so this is orbitals overlap occur. So this already I have told you. This is what, top of a band, there is lower S band, which is if the bonding interaction becomes weaker. Towards the left hand side of the graph that we have seen, P band will, so critical interaction, the crossover point, as the interaction strength necessary to involve S and P equally in the bonding. So that point we have already discussed. So, and then we also see, so, who is there? Somebody was knocking. अच्छा, ठीक है, फिर हम इवनिंग में लेंगे एक तो। Thank you.